more of a try to see how things work. But I had a bad COVID last week. So till yesterday, I was mostly in bed. So that part hasn't worked very well either. Also, if I just fall asleep, forgive me. Okay, so that's the background. Now, I have seen some of the talks today. They're very beautiful and very nice. As opposed to them, I don't even have a picture. And there are going to be lots of equations. So just take it as an end of the entertainment, if that is how your entertainment goes. And then stop me any moment and ask me any question. It's just a learning experience for me. So bear with me. Okay? I will try to avoid all jargons. And whenever there is a jargon, I will try to explain it. Okay? Is there something to point with?
You can use
the mouse?
Yeah, use the mouse because
no, don't worry. No, it's okay. So the whole thing, the reason I got interested in neuroscience is because Arvind is a friend and he corrupts people. So when I talked to him about various problems, I thought of two things that I think seems to be some gaps in how neuroscientists are thinking about their field from the point of view of a physicist. One of the things I would say is that any biology is always a non-equilibrium physics problem. Because if you are in equilibrium, you are dead. This was discussed way back in Schrödinger in a book called What is Life, which physicists think made a huge impact in biology. But the biologist doesn't think that. but nevertheless, so I think one of the things that is being done in neuroscience and has been done in neuroscience has not taken into account the fact that a lot of the phenomena that are happening are outside equilibrium. And I think there is a lot of space for looking at neuroscience from the eye of a non-equilibrium physicist. But that's not what I'm going to talk about. The second thing that also looked interesting is that, well, the neuroscientists know pretty well how one neuron functions. To me, this looks like an amazing achievement done over many years, the Hodgkin-Huxley equation, really fantastic thing. And now the problem is there are lots and lots of neurons. They are connected in ways that are not very precise. And how does this collective system behave? And there is a lot of work on this. One thing that is missing in this piece, to my eye, is that there is a lot of inhomogeneity in the neurons. Two neurons are not the same. They don't have same action potentials. They are not connected in the same way. And how does this inhomogeneity taken into account in the kind of pictures of large-scale neural problem that you are dealing with? And the whole purpose of today's talk is to show you that there is a systematic way, although quite from distance may look quite tedious, there is a systematic way to deal with this kind of problems in theory and to extract meaningful things out of them. Okay? So I start with what are called neural field models. I guess all of you know this. So the U is the potential in a brain or in a connected set of neural networks. It's at a scale where the U actually includes many neurons. So in the language of us, we would think that this is a coarse-grained picture where one dot in my model contains many, many neurons inside. There is a whole history of this being done in statistical physics, where you typically say that I have, say, some condensed matter system with electrons and nucleus and so on. And in this system, I am measuring magnetization, the magnetic field at a point, which is, of course, not coming from one electron spin. It is an average quantity of things which are coming in its neighborhood. So it's in the same spirit. I'm looking at a length scale. And in that length scale, there is the potential U. And there is an equation for it. Now, has this equation been derived starting from the equation of one neuron and many couple neuron and systematically? Of course not, because that would be a too complicated problem. However, even at this level, if I think that one point in my model comes from averaging over a whole bunch of neurons, even that point and its neighboring point will have slightly different properties. So that's the main theme that I am going to work towards. That if you have a model like that, which is quite nasty to a mathematician's eye, because, okay, left-hand side is nice, you have just a first-order derivative in time, but the right-hand side, you have a convolution. So there is some function over u, and this function is typically something which is not a simple linear function. And then it is multiplied by some weight function w, which basically tells you how far the effect is. And then there is an integral. So this is the convolution. So you could say this is the integral differential equation. Now, these are nasty things. One should spend their life trying to avoid them. But when you have them, you have them. There is not much you can do about it. So how do we analyze this kind of things? Are there ways to analyze this kind of things? Of course, you can put it in a computer and run your computing power at it. Yes. But that gives you number, not always insight. So the goal is to look for insight, not necessarily numbers. One can't live without the other, of course. Okay, so the other thing that I want to mention is the connections here are local by construction. The function w, which tells you how far one neuron's connection goes, is a function that doesn't go very far. It has a cutoff. Okay, so in the sense of some of the models that I had heard today, where there is no space, the network has no concept of distance, and some other models where the network has a concept of distance. This is more of a network that has a concept of physical distance. It knows its neighbors. Okay. So that equation that we had can be turned into a PDE, a partial differential equation, which is better. And this works, for example, in the following way. Oh, this is really slow, I'm sorry. So you can say that I take the function u, I take the variable u, which is a potential in space and time, which is just a field. And then I multiply it by the function f, which is the activation function, which will have a cutoff and so on. And then I multiply it by a kernel. And that kernel connects in space and in time. Time connection is very complicated. So I will drop the time connection. People have done that. They basically change the time to something which is delta function in time. That means it's just travel with a constant speed that you can see here in the last term. My mouse. And there is my mouse. Maybe I should turn it into a bright dot. How does one do such
connection?
Sorry?
There's a lag through Zoom, I think.
I see.
Isn't that one next to arrow?
Yeah. Thank you very much. Yes, I have a laser pointer. Okay, so there is this kernel. So that kernel is some function of space, w, and in time it's just like a traveling wave. And if you turn the space dependence into an exponential, then you can simplify this. And after simplification, you will get an equation like the one below. This one, you see a partial differential equation. There are second order time derivative. There are second order and first order time derivative. And there is a second order in space derivative. Okay. So, okay, not too bad a thing. So these kind of problems have been analyzed and people have shown what they contain. So they contain traveling waves, which was practically included by hand into the problem. Then they contain patterns, and there is a certain style of analyzing them. And the style of analysis goes something like the following. You first start with a solution. Sometimes it's just a constant value. Sometimes it's often just a trivial solution. Okay. And then you say, I want a small change about that solution, and you linearize the problem. once you linearize the problem, then you have a linear problem at hand. You can look at the stability of that linear problem. If that linear problem is unstable to particular perturbations, then you will see that kind of patterns emerging in your system. Of course, that's a pattern that is unstable, which will grow in time. So you have to also ask the question, how does it saturate? And that you can try to handle by what is called weakly nonlinear analysis. Okay. So that's the way people have done it before. And these are the weakly nonlinear approximations that work has been used to investigate these problems. Whereas we will talk about an alternative technique, the renormalization group, which we will come to. But before that, I will somewhat simplify the equation. So start with an equation for phi, okay, which has a simple time derivative on the left. And there is some function L of phi, which is local in phi. So you say that phi itself is excited by a certain function. Then there is a function, there is a convolution, the same W, which we will simplify again and then get all kind of derivatives. And to this, we add a noise, okay? So there is a neural field and there is an externally driven noise, which is perfectly normal. Your brain is being driven by noise all the time. And this noise, which is I, is a function of space and time, but it is white in space and white in time. Okay, it's not correlated in time. It's just a thermal noise. If I now expand the function f and L in a Taylor series, then I will have a lot of terms. I will practically get all different kind of operators. For the moment, I will just keep a class of them. As you can see below, over here, so del T of phi, there are all these functions which goes as phi to the power n, which comes from expanding the function L. So there is linear in phi, quadratic in phi, every other higher order in phi. And then there are functions which are del square over all such powers of phi. And then in principle, you could have del 4, you could have del 6, and all kind of possible operators. So within this framework actually lies lots and lots of differential equation. That's normal because your function W and the F and the L are all nonlinear functions. And we have just expanded them in Taylor series. Okay. So this is a stochastic. It started with a stochastic integral differential equation. We turned it into a stochastic partial differential equation. But this is a nonlinear beast. And how do we extract large-scale properties of such equations? So it is still stochastic. So what does it mean by solving a stochastic problem? If I give you a differential equation, you solve the differential equation. What does it mean by doing that? If I tell you that, look, this differential equation describes a physical system. That physical system starts with this initial condition. After a certain time, the system is going to be there. You can solve the problem and say, yes, after that time, the system is precisely going to be there. Now, if it is a stochastic equation, what does it mean by solving it? Because every time you solve it, you are solving it with a different realization of noise. So you are getting a different result. So what does it mean by solving a differential equation, a stochastic differential equation, is to actually find out the probability distribution of solution. You can say, okay, look, the probability of this particular solution to appear is this. Probability of that particular solution to appear is that, and so on. Okay. So the best you can do in a problem like this is to calculate the probability distribution of all possible solutions. Okay. Think of a moment how nasty the problem is, because your solution is a function of space and time. So the solution is going to tell you what is the probability of certain function of space and time to appear as a part of your solution. Okay. So as you know, all nonlinear problems cannot be solved. It's basically as simple as that. In very few cases, they can be solved and they are very special. In general, they cannot be solved. So what do you do with a problem that you can't solve? You basically say, I will do perturbation theory. Okay. And maybe I can do something to handle the problem by slowly creeping towards its solution. That's what people do, a physicist or an applied mathematician and so on. So we start with the simplest case. We start with the simplest equation. Del T of phi is some constant times del square phi, which is just the diffusion equation, plus a noise. It turns out that physicists have dealt with this problem before. This is what is called Edwards-Wilkinson model. Not important. Just that we know the answer, and it's a pretty simple model, right? So you can solve it by Fourier transform and so on. But let's do something else, which is a very powerful and very underappreciated technique. It's the technique of scaling. See, we have to solve this problem, nonlinear, complicated, that we cannot do. So we have to let something go. The idea is you give up the idea of knowing about this solution in all detail, but you ask, how is the solution going to behave at large scales in my system? Okay? So then you have to choose to look at the large scales. This idea of looking at the large scale is built into the whole problem here. It also makes sense because if you are looking into small scale, then the results that you are going to get are going to depend upon whose brain you are dealing with. And that's not what you want. What you want is, are there some general questions that I can answer about everybody's brain? Okay. So the thing you do is, let's say you scale your length by something, by a factor of b. Okay. Take every centimeter and turn them to inches. If you do that, let's say you scale your time also by a factor of b to the power z. We don't know what z is. Once we do that, the solution phi also changes. It picks a factor of b to the power alpha, and we don't know that either. And the noise itself changes. It picks a factor of b to the power lambda. Okay, the factor z, z, alpha, lambda, I don't know. But we will look at the equation and we will demand that under this rescaling, the equation, the nature of the equation remains the same. If I impose that on the problem, if I assume that the whole equation remains scale invariant, what are the relation between these exponents? It's just simple power counting, so bear with me. If you look at the equation for the noise, okay, so what happens when I scale things? The right-hand side has a delta function. Remember, delta function has a dimension of 1 over d, okay? So when you scale length x by b, the delta function gets a factor of minus b times d. And then there is a delta function in time, which is minus b to the power z. You put them together, and the left-hand side gets a factor of b to the power twice lambda. If this equation is supposed to be scale invariant, you will get twice lambda is minus of d plus z. Okay, that's the first relationship. No, I think this is easier. Okay, twice lambda is minus of d plus z. Okay, now look at all the terms in the same equation. So what is this del t going to pick up? Del t is like 1 over time, right? And time picks up a factor of b to the power z. So this is going to pick up a factor of b to the power minus z. Multiply that by everything. Everything picks a factor of b to the power z. Okay. The phi picks a factor of b to the power alpha. This also picks a factor of b to the power alpha. So they cancels, but the I gets a minus alpha. Okay. So the del square, remember, is like 1 over length scale square. So that will get a factor of b to the power minus 2, which gives you b to the power z minus 2. Just do the simple power counting and demand that this equation is not going to change. You will get z equal to 2, lambda equal to z plus d by 2 minus, and alpha is 2 minus d by 2. What does this mambo jumbo mean? So now let me remind you what we are after. We are after the probability distribution, right? So what is telling you is that if you change your length and time in a certain way, you scale them. When you look at the large scale, you are basically doing the same scaling. And if you want to, and you say the answer that will come up will obey a property like this. What does it mean? That if I take phi and correlate it phi at a different point, Okay, if I look at the phi-phi correlator, the correlation between 2 points in the neural field, then you will naturally ask, how does this correlation change with space and time? And it will go as space to the power 2 minus d by 2 and time to the power 2. Okay, so the problem is solved without doing anything, just by power counting. You could get the same answer by solving the problem by Fourier transform and so on. Okay, it's not telling you what the function is, it's just telling you how those functions change. Okay, okay, so that's so far so good. Linear problems solved cleanly. Okay. Now what happens if I throw in all the other new terms? So I assume that this part of the equation that I dealt with is going to remain the same. And all the other new terms that I could throw in, I want to ask, how does those terms behave under the same rescaling? Why do that? The idea now is, you can now, as you see in this problem, there are all kinds of functions. Maybe as you go to larger scale, some of those functions are not important. Are all kinds of functions important as you go to larger scale, or some of them not important? This is an extremely important part of thinking about the problem in this way. Okay, so you can do the same power counting, but this time, you see, we had this part of the equation, and we have now added all kinds of terms. Okay, all terms which are phi to the power n multiplied by an and bn del square. I can use the same scaling that I showed you. I can put the same scaling behavior. And in the previous slide, I know the value of z, I know the value of alpha. So I put them back, and then I check, do these terms grow or do they decay? If you look at that, whether they grow or decay depends on your dimension of space. Now, what is the dimension of space a neural network lives in? It's not really 2D, as I was looking at pictures today of cuts of our brain. Well, hopefully not our brain. Maybe it is not completely 3D either. At the moment, we can think of a general dimension. Okay? So if you simplify things, then you will realize that d equal to 2, all of these terms actually goes to infinity. So none of those terms can be ignored. If your model had a very small amount of those terms, and you go to larger and larger scale, those terms are going to dominate the problem. That's first thing. If you had a whole bunch of these terms, the same thing is also true for d equal to 2. They will also all grow. So you cannot cut off the model at any term. You actually have to deal with a whole complicated model like this. That's the first lesson. Okay, but now how to deal with this? I can't tell you how to deal with this in a short talk like this, but I will try to give you a flavor. Okay, bear with me. So as I told you, the whole idea was that solving a stochastic problem means solving for a probability distribution, right? Now, for every probability distribution, there is a moment generating function. The moment generating function is the Fourier transform of the probability distribution. So if you know one, you know the other. So for the moment, this problem tries to work out the moment generating function. And the moment generating function is typically written as this kind of a fancy Z. Okay? So let's start with a general equation. Some operator over I is equal to noise. Okay? This operator can be a spatial operator, temporal operator. Let's put everything in there. Okay? And I want to find out what is the moment generating function of all the functions that are generated by this equation. Okay? So the moment generating function is an integral of all values of the function. But what does this function need to satisfy? These functions, of course, need to satisfy the differential equation itself. So I put that with the delta function. So it's integrate over all functions who satisfy this relationship. Okay? But that's not enough. all of them also need to be driven by the noise. And the noise is a statistics. The noise is a Gaussian, and its correlation function is D. Okay, so if you now write this for one value of the noise, you have to integrate again for all possible values of the noise. Okay, so then you obtain this integral. So essentially, this is a solution of the equation averaged over all possible values of the noise. And the noise is Gaussian, so you can average over a Gaussian noise. It can look technical, it can look complicated, but it's plausible. Okay, so it's looking nastier because what we are dealing with are not functions, are not function of many variable, but function of space and time, right? Let me just, as you are not complaining at the moment, let me just step aside, okay? Feel free to complain. Okay, so this looks complicated, but because it's a Gaussian function, because it's an integral over a Gaussian, this integration can be done. Once that integration is done, this quantity, the moment generating function, will turn out to be something like this. So what kind of object is this? This is integral of exponential of something which has a variable capital phi and small phi. This one, the capital phi emerged because I integrated over the noise, okay? And use this delta function. See, to impose that delta function, you need to introduce a new auxiliary variable. And once you do that, now you notice in this that this is a quadratic, this is linear, and this one is as complicated as it wants to be, because that comes from the actual equation you started with. Okay? Okay, this all looks weird. So I'll give you a simple example just to remind you of Gaussian integrals. Right? So who remembers Gaussian integrals? Thank you. Who has seen Gaussian integrals? Great. Thank you. And whoever hasn't can easily check Wikipedia. These are fun things. So I have an integral which is e to the minus some y square plus some lambda times y. Okay. You can integrate this, and the result is this: twice pi by c to the power half e to the lambda square by twice c. There are various ways to do it, some nice, some not so nice. Just have fun with it. Okay. Now, but if you want to integrate something like this, let's say y to the power m and multiplied by the Gaussian. Why would you like to do something like that? So if your probability distribution is Gaussian, and then you want to calculate the mean, then of course it's y multiplied by the probability distribution. If you want to calculate the standard deviation, it is y square multiplied by the probability distribution. If you want to calculate any other higher moment of your probability distribution, is y to the power m multiplied by that. Now, if you know all the moments, you know the moment generating function, and you know the function itself. So this is the approach to it. Now, if you look at this, there is a nice trick in actually calculating this integral. The trick has to do with the fact that if you realize that, don't worry about the first factor. If I just take this integration, this integral, and differentiate it with respect to lambda, then I get a factor of y on the side. So y to the power m is actually m derivative with respect to lambda. Okay? And that gives me the solution of z, but then I have to divide by z. So this becomes log z. So any moment generating functions like that are mth derivative of the log of the z. Okay? So, good. So now if you take this lesson from one Gaussian integral to the kind of problems I'm talking about, see, these are the kind of quantities which are trying to integrate. And to obtain them, what we need to do is to actually take a log and then take derivatives. Of course, we can't do that. That's all very complicated. Now, there is a trick that was invented. So this kind of problems have a long history. They appeared in physics in quantum field theory, in the kind of problem that Feynman, Schwinger, and Tomonaga solved. And there were certain tricks called renormalization that were used to patch up infinities that were appearing in those problems. Much later in the 70s, there was a better systematic way of dealing with these problems due to Wilson. And this is an idea called renormalization group, or RG. And I will give you a little bit flavor of that idea. And the idea is the following, that we had this field, but we are interested in the large scale property. So let's look at the Fourier transform of that field. Okay. Now, large scale means small Fourier mode, and small scale means large Fourier mode. So once I do the Fourier transform, my variable phi, I can think of it in Fourier space as things that are small scales or large wave modes, or large scales or small Fourier modes. Okay. What I want is an effective theory for the red ones integrating over the green ones. Okay. And the idea is I cannot do this. So Wilson came up with the brilliant idea that to actually do this in a way, and that's the whole trick of it, to do this integration over a very small shell. Such a thin shell that all the integration basically is over this constant shell. So you just need to do angular integrals and nothing else. Now, once you do that, you get some new quantity as a result of the integration. And you say that new quantity is going to change all the constant in my theory. And then I'm going to repeat this over and over. So as I try to come to the center of my problem, which is my large scales, what I am going to see is that the parameters that appeared in my problem that I started with are going to change. Okay. They integrate over a very thin shell, absorb the result into the coupling constant, and rescale to get the original domain back. Rinse and repeat. And the coupling constant are changing and they're flowing under this process. And you want to ask what is the property of this flow? This is what is called the RG flow. So recently this appeared in a neural network contest in PRL, which is how we got corrupted by this. And the model that they dealt with was this one. So this is the del square operator. So you see this is similar to our model. And what you realize here, let's have a look at this. Okay, it's a simple equation. It's del square of h, del square of h square, del square of h cube, plus a noise. So this is not a very nice one either, because this is a nonlinear equation. This is nonlinear, this is nonlinear, right? So when you apply this technique to the problem, then you ask what happens when I go to larger and larger scale, or smaller and smaller vector, smaller and smaller wave numbers. The idea is that you have these coupling constants, G1, G2, G3. They change as you change your scale, okay? That there are technicalities in finding how they change. Once you do, then you make a plot like this, okay? You can see how the constants are flow, okay, in a particular dimension. And from there, you can ask, what is my large scale property is determined by, for example, the fixed points of this flow. Okay. That's the idea of perturbatively trying to extract large scale behavior from complicated partial differential equations. But I still haven't told you about the inhomogeneity in the problem, right? So far, it is just partial differential equations, but there is something more. So this is something I picked up from Arvind's paper. So what happens when you try to introduce some inhomogeneity in a neural problem? A lot of things happen. This is a simple case. So you have a lattice, But in that lattice, you have introduced an inhomogeneous rather than anisotropic behavior, where you say the connections are not uniformly in every direction. The connections are more probable in one particular direction. And then there is a noise, and you can choose different realization of the noise. And depending on the realization, you can get many different kinds of feature appearing in your neural network. And the idea of a calculation that we are talking about would be to extract the right pictures from a theory of the left pictures. Okay? Okay, so where is that coming from? So let me go back to the simple model that we were dealing with. There was an equation for phi. There is just the del square operator. There is some constant. There is noise. To that, I add another term. This term multiplies by an m, and this m is a noise. But this is a very different noise. So just spend 2 minutes with me thinking about this noise. Okay? So you can think that there is a noisiness in our brain. Of course, there are thermal fluctuations, there is blood running inside, there is all kind of noise being created. But your brain operates by averaging over all such noise. But there is a different kind of noise between my brain and yours, because each one is connected differently. And these two noises are very different in nature. One is the noise that is fluctuating over small scale, and any behavior appears as averaging over it. The other one is peculiar to you and me, right? It doesn't make sense by averaging over noise over all our brain. So what does it mean by taking the average behavior of a system where there is sort of what is called quenched randomness? See, because these connections in our brain, they change, of course, but they change very, very slowly. And it is these plastic connections that we are talking about, how to take them into account. So how does one average over those quantities? And what does it even mean by averaging over those quantities? Okay. So
someone wants to answer that question.
I thought I said something wrong. Okay. So I was talking about the noise. So now that we have the noise, what does it mean by averaging over this noise? So you can say that this noise is something which is there, but over the large scale, this thing becomes uniform. So going to large scale is one kind of averaging over this noise. Such a thing is what is called self-averaging. Okay? But there is a trick to that, which I will come to. But you remember that the actual moments are calculated by derivatives over the log of z, not z. So what you need to average is the log of z, not the z. And averaging over log of a quantity and log of an average are, of course, not the same thing. There is a trick invented called the replica trick by Parisi, who basically said that, look, you can use this formula. Log of z is z to the n minus 1 by n in the limit n going to 0. So take many copies of your system and calculate z to the power n. Then average over that, then take the limit. And presumably you will get the right answer. Not always. There are some cases where this goes wrong. So just to show you what we did then is the following. So as I told you that I need to take the equation and take n copies of the system. Okay. So I have n copies of the system. I had the z and I take it to the power n. Then in the exponential, of course, everything gets summed, right? And then once everything gets summed, you remember there was this constant G0 which multiplied the m, which is this m, and you have a term like this, okay? Now, it is this m that we need to average over, but this one has all this kind of couplings there, okay? So this averaging is now over m, okay? You can do that by assuming m to be Gaussian. But remember, you have to average z to the n, not z. Okay? And then once you do that, you get something like the following. You get whatever thing you started with, plus something where the noise has been averaged. So what appears is the noise correlation. The noise correlation function is the capital M, and it has now developed 4 legs like this. Okay? So what does that mean? Remember, the noise appeared linear in your problem, but after the averaging, it has given a new nonlinearity. This is looking technically difficult. I have not immediate easy way to show you how. I can do it in 10 minutes over board at some other point. For the moment, just bear with me. So one important thing that comes out of this is that if a noise which is quenched in the system appears even in a linear way in your model, after averaging, you will get a new kind of nasty nonlinearity in the system. And then you can deal with that nonlinearity. You can do the kind of integrations that I talked about using a thing called Feynman diagrams, which we don't need to worry about at the moment. But all that I want to say is the following. So I don't know what looks better, these are the equations. Once you try a little bit to learn these diagrams, they are way much better than writing equations. At least they're more stylish, and people are more confused. Just to tell you a little bit about what is happening, you remember we start with an operator called L, right? And now I'm saying that if I now start integrating over the wave number slowly, then to the leading order, this operator is going to change. This operator is going to be the operator before, plus something else, plus something else, and many other things. Okay? This is the noise. And the noise is the old noise, plus a little bit, and then there are many other things. And then this was the noise that was inherent in the quenched one in the brain. And it is that noise, which was the original one, plus other little pieces. Okay? It's just a systematic way of doing a perturbation theory. Once we do that, then we get a set of equations of how my coupling constants change. So remember, I talked about 2 models. One model where the noise appears like this, some noise multiplied by the variable itself, and the other case where the noise is a vector, like Irwin's model, where the noise points a direction, and this direction is different in different places. So it appears as m dot some gradient over the phi. Okay? And you get 2 sets of flow equations in 2 cases. Don't worry about the omega, that's why I just removed it. But there is one important thing to see here. The quantity that is beta here essentially is the coefficient of diffusion. Okay? What you realize is on the right-hand side, there is a 1 over k square factor. Now, remember, we need to go to the limit k going to 0. That means this number is going to be infinitely large. Okay? So the whole calculation is giving me something which is going to actually blow up. So the technique that we are using is not good enough to deal with this kind of problem. Okay? This kind of things happen in these. These are typically what are called infrared divergences. And that just spoiled my calculation. Okay? However, for this model, this is not true. It doesn't blow up. Things remain nice. And I can actually calculate the flow equation. So just to tell you or things maybe you could remember from the talk, we have a method which is the replica renormalization group to extract large-scale behavior for inhomogeneous neural fields. The method is a work in progress, as I showed you, because some cases it gets infinity. There are other techniques to deal with this that I'm not going to go into. In the model A, which is the one I talked about about this is it fails. In the model B, it works, and it shows how the quenched noise modifies the large-scale dynamics. Thank you for your patience. And if there are questions, I'll be happy to answer them.
Yes. So in the case in model B, right? So when you take into account inhomogeneity, right?
Yes.
The one, which is the one that
Absolutely, yes.
is converging, right? You don't have the flow yet.
We have. Those are the flow equations.
Okay. So you don't have a picture, right?
Yes.
No, you don't. You do?
I haven't shown it. I have a picture, but all the implications are not yet clear to me.
Okay. So there is a fixed point.
There are fixed points,
Yeah.
yes. There are fixed points and things, but then there are stable and unstable fixed points. And what exactly they mean is not yet completely clear. Yes, please.
I have several questions, but
Please.
I hope I don't. Yeah, so one is our brain is finite, so is it really a problem that it doesn't converge for k to 0?
That's a very good question. So this kind of problems also appear, say, in statistical mechanics. And of course, the amount of molecule is also finite. But the number of molecules is still 10 to the power 23. So the way we typically talk about it is that we say we first take a finite box, and then we let the box go into infinity while the density remains constant. So this is what in our language called thermodynamic limit. If we take the limit here, the integrals will actually diverge. So the problem exists, but the problem is that it is a problem of the technique. It's not a problem of the system. Because you see, because to deal with a system, I made a perturbation theory. Each piece of the perturbation theory may actually go to infinity, but they may cancel each other. And I don't know how the higher order terms behave. So this is a pathological nature of how I have approximated my equation. I have to find some better way to do it. There is no real problem.
Yeah, okay, thanks. And another question I had was, how do you, or has it been checked in any way, or would you like to check if there is this scale invariance in the brain, so that like, is the shape of the equations the same at the different scales really in the brain?
I think that is much more difficult to check if the equations are the same. But what one would check is that if I calculate the correlation function of the potential, can I reproduce that coming from my theory?
Yeah.
So if the correlation functions have a power law dependence, then of course it is scale invariant. And then it makes sense to approach it this way.
Yeah.
But if they are not, then of course it doesn't. But any power law has cutoffs, right? So I don't expect it to happen at all scales. I expect it to happen within a range of length scale.
Yeah, yeah. The final question I had was about the determining the effective dimensionality of this system.
Right.
How would you go about it?
I don't know. At the moment, I can just, dimensionality is something you carry over in the problem.
Yeah.
But the dimensionality plays an important role in the following way. It tells you, for example, that there may be a dimensionality above which your problem will become simple, or below which your problem will become too difficult. Things like that. So that's the use of the dimensionality in this problem. Sometimes you can use the dimensionality itself as a perturbation parameter. You can show that, for example, in certain problems, you can show that the problem becomes solvable in 4 dimensions. Whereas, of course, you are interested in 3 dimensions. But you include 4 minus d as a perturbation parameter, and then calculate a perturbation theory from that dimension.
Yeah.
Whatever makes the calculation easier.
Thanks.
Thank you for your patience. Yes, please.
So on a high level, so basically the neural field models usually have like a kernel that
Yes.
depends on the distance from the neuron, which tells you about the coupling strengths.
Yes.
And this is usually the same throughout the
Right.
field, right? So everything somehow, you have a homogeneous
That's right. Yes.
field.
Yes.
And now you want to introduce that anywhere in the field it could be different.
Yes.
And this is the inner.
This is you should have given the talk. But honestly, yes, excellent summary.
That's all I could say, unfortunately. But so I'm glad that you gave the talk. But would you link this version of the model back to the? So I think I don't. So the M is the.
So let's
Maybe I'll let you.
let's look at this one. No. Thank you very much. It was a brilliant summary. So in the neural field model, this could be a complicated function and all kind of nonlinearities. To understand how the problem changes, I kept only the simplest one, which is just diffusion. Then I added this term, which is a vector M, which tells you the local inhomogeneity of the kernel, local anisotropy of the kernel. And this is different in different places. But averaged over the whole thing, this will go to 0. So that is the model. And then I assume that I know the statistics of the M. Otherwise, my problem is not defined. Once I know the statistics, then I can ask what is the large scale behavior of this system because I included this. And the first lesson is, because I included this model became effectively nonlinear. So in addition to the nonlinearities that would normally be in the problem, by making the kernel anisotropic, we will introduce a new kind of nonlinearity. That's the first one. Second is that new kind of nonlinearity can be dealt with. In some cases, that nonlinearity will actually go away. And the model will go back to the usual model, which is a good case where we can say that even if there is a small inhomogeneity, that's not going to matter. But in other cases, that's going to give some new behavior.
Have you done all this now for Arvin's
No.
correlated? Not yet. Okay.
No. We have done it for this very simple case so far. Putting it together will take some time.
Okay,
Thank you very much.